Okay, so last time we added this LDI to the accumulator instruction, which basically allows us to put an immediate value or a value that's hard-coded into the instruction into the accumulator. So now we have a much more useful computer. Not only can we add things to our accumulator, but we can also put hard-coded values. We can initialize the value of the accumulator. Okay, so that's cool and everything, but I think the kind of the next piece here is to start allowing us to have more variables. Right now, the problem we have is that we really only have one variable here that variable gets stored in the accumulator. Okay, so if we want to write a program that's more complex, we basically can't really have any programs right now that have more than one variable in them, right? So we want to kind of try and fix that. So what we're going to do is we're going to use a memory to store more variables. So let's go over how a memory works real quick here before we get started. Okay, so in one of the first videos we did, we used this ROM. And this ROM basically is going to store our program, right? So this ROM is great. ROM stands for read-only memory, and it's good enough for demonstration purposes to store our program. It's super, its contents are super visible here, which is one thing that I like about the way that Circuitverse does this, right? You can really see exactly what's going on inside of this memory, right? But the downside of this is that it only has 16 locations, right? There's only it's like an array with 16 elements in it, and it can't get any bigger than that. All right. So the other thing is it's read-only, which means you can't write to it with the hardware, right? The only way you can put new values in here is by clicking on it in the Circuitverse thing and typing a value in by hand, right? There's no input on this memory to allow us to write new values into it through the hardware. So it's not really going to be a good tool for storing variables. So we're not going to use that. We're going to use a different kind of memory called a random access memory. All right. The random access memory here, you'll see it has a few more ports on here. It looks a little bit more like a register. All right. So the random access memory is similar to the ROM, except it has this address input here that allows us to select which which location we're going to be reading or writing to, right? And it has a data out that's going to spit out the data that we're going to read. But it also has these two additional ports, data in and write enable. Okay, so the data in allows us to write a new value into the memory at some place, and the write enable allows us to either read from the memory or write to the memory. Okay, so we have two modes of operation for this RAM. We can either read from it. So if we're going to read from it, we're basically going to just put an address onto this address line. Okay. So let me just modify this so that we have a 4-bit value here, and the address width, we'll make that 4. Okay, well, no, we'll make the address width 8. There we go. Okay, so we have 256 locations in here because there's 8 bits in the address, so we need to make an 8-bit address. Okay, and then we're going to have a data out, which is going to spit out the data at whatever address. Okay. All right. Oops. Okay, cool. All right, and then we're gonna set the write enable to 0. Okay. So now what we're doing is we're giving it an address of 0. We're asking this memory, what do you have in your memory at address 0? And it's telling us the value at address 0 is 0. Okay? What if we wanted to write a new value at address 0? Okay, what we can do is we can put a data in on this thing. And let's say we want to write the number 1010, which is 10 in decimal. 1010 binary, 10 in decimal. Okay. So what we can do now is we can set the write enable to a 1 and then put it back to a 0, And what you can see is that it has held that value 1010 in memory at address 0. Okay, so now what we've done is we've actually written a value. We've stored this value 1010 binary at address 0 in this memory, and now we can go to a different address, and you'll see that the data at a different address will change. If we read from address 00000111, that is address 7 in our memory, and address 7 in our memory holds the value 0. Okay, so but if we go back to address 0, if we're like, oh, okay, I want to look again at that variable value that I just got done writing, you can see that the variable at address 0 retains the value that we wrote to it, which is 1010. Okay. Okay, but let's say we want to go back to address 7. That's 111. Address 111 in our memory, and we're going to write a different number to this. Let's say we want to write 0101, which is 5 in decimal. Okay, so we will click the write enable and activate the write enable. All right, and then now we have written the value 0101 at address 7. So we can go to a different address in memory. Let's say we go back to address 0. You can see that address 0, we have 1010 at address 0, which is a number 10. And if we go to address 7, we have 0101, which is 5. Okay, so this is the way that we store variables, right? Each variable in our program is going to be assigned some address, and when we want to write the value to that variable, we're going to give it a new value on the data input of our RAM, and we're going to set our write enable bit to a 1, right? So let's say we want to change the value. Let's say I've gotten to some point in my program and I want to change the value of this variable that lives at address 7. Now I want to change it, instead of 0101, I want the new value to be 1111. That's okay, we can do that. So we're going to click the write, and then what you can see is we have updated the value here in our RAM. And then we can always go to a different address, read the value of a different variable, and if we come back to that address that we were at before, then you can see that the variable's value has not changed. Okay, it retains its old value. This is how computers store variables, right? Each variable, you give your variable a name in your program. You might call it I or something like that. And then the compiler assigns that variable an address in memory. And then it always refers to that variable by the address that it assigns. Okay. The problem we have with our computer right now, though, this accumulator machine that we've been working on over here, is there's no memory, right? We only have this accumulator. This is the only place that we can actually store anything in this processor, right? We don't have any memory that we can actually use. Okay, so what we want to do is we want to add a memory to this processor, so that we can actually store some more, some variables and write more complex programs. So let me take this memory that I've created. I'm going to put it over here. I'm going to put it about right here in my processor. Okay, great. So what we need to do now is we need to hook up the address and the data in and the write inputs here for this memory, so that at least we can write to our memory. Okay, so we're going to create a couple of new instructions that are going to allow us to write to this memory. Okay, so in order to present data to this memory, we need to be able to present an address and present the data that we're going to write to that address. Okay, so what I'm proposing that we're going to do here is we're going to use the accumulator. Okay, the accumulator is going to be the source of the data in. All right, so I'm going to just hook the data in directly up to the accumulator. So the only place we can write to this memory is from the accumulator. Okay, this is a very simple processor. All right, but what about the address? Okay, the address, we don't really have a good way of presenting an address to this thing, so we should probably figure out how to do that. And the way we normally do that is most processors have another register called the index register that allows them to write to their RAM. okay, to write to their memory. Okay, and so so we'll do that too, right? We'll create an index register. So the index register is going to be just like the accumulator, except it's going to be used as the address input for this RAM. Right, so if you look at this RAM, the address input here, the way I've configured it with an address input width of 8, which means the address is an 8-bit bus, right? So so we need to have whatever input we give to this thing needs to be 8 bits wide, right? The challenge we have with doing that is that the accumulator is only 4 bits wide. Okay, so we really need to have like 2 registers next to each other to create, so 2 4-bit registers are going to be used to create this 8-bit address. Okay, so let's place that. So we'll insert a new sub-circuit. We'll use a 4-bit register here, and this is going to be our index register right here. This is our index register. Very good. Okay, so the index register then, each one of the outputs of this index register, these Q outputs, these are both 4-bit outputs. So what we can do is we can just basically kind of glob them together using one of these splitters, right? So we have, this is going to be the low order 4 bits of our address, right? Bits 3 down to 0. And this one here is going to be the high order 4 bits of our address, bits 7 down to 4. And together they're going to create an 8-bit address that can go into our RAM. Okay. All right, very good. And then basically we just need to take this this write enable port here. Somehow we need to enable this write enable port. Okay, we'll get to that in a little bit. But for now, before we start worrying about this write enable port on our RAM, we should probably try and figure out how can we actually get a number into our index register. So at the moment, we really don't have any mechanism for putting a value into the index register, right? Before, we had previously, in the last video, we talked about using the LDI instruction. We invented this new LDI instruction for putting values into the accumulator, but we don't really have any equivalent way of putting a value into the index register, right? We need a DIN. We need a D. Basically, the main thing we need here is a DIN on this thing, right? And then of course probably a write enable and a clock and a reset. So the clock and the reset are fairly easy. I guess we could probably just hook those up right now. Let's do that. And I'm going to be careful to make sure I keep everything super neat here. I want all my wires to be neatly organized. I'm going to create some space so that I don't have a ton of, I don't have a big rat's nest of wires here, right? That's my goal. So all the registers in this thing share the same clock and the reset signal. Okay, the write enable signal from these guys is going to come from our decode logic, right? So basically the decode logic is going to look at the instruction and it's going to try and figure out, is this instruction writing to our index register? Okay, so we're going to give these 2 index registers here. These are kind of like 2 separate registers in our processor. We're going to give them two different names, okay? This one is going to be called L for low, and this one is going to be called H for high, okay? We call this one L for low because it represents, or it stores the low order 4 bits of the address, of the 8-bit address, okay? And H stores the high order 4 bits of our 8-bit address, right? So what we want is we want to take the value, we want to create two new instructions with two new opcodes. Okay, one of those instructions is going to take the value that's in the accumulator and it's going to transfer it to the L register. Okay, so here's my D in port for L, and I'm going to take that D in port and I'm going to just tap it into the accumulator's output. This is the output of the accumulator here. Okay, so that's what that instruction is going to just, we're going to have one new instruction which is going to take the output of the accumulator and transfer it into the L register. And we're going to have another instruction which does the same for the H register, right? So we can basically generate an address by using an LDI instruction to put an immediate value into the accumulator. And then we can transfer that immediate value using a move to L or a move to H instruction to generate a full 8-bit address by transferring the accumulator value into the L register or into the H register. Okay. Alrighty. So now the last thing to do is we just need to enable this write enable port here on our L and H registers, right? We need to hook this up in our decode logic. So let's go to the decode logic and take a look. All right, so I'm trying to keep track. I'm trying to keep this as neat as possible. So maybe I better just save this thing real quick here. Okay, so I'm trying to keep this. I'm trying to keep this as saved as neat as possible here by just recording what the different opcodes for my instructions are. Right. So if you recall from the previous videos, the 0000 opcode is an add immediate to the accumulator. 0001 is a load immediate to the accumulator. And then right now, today, we're going to create these other two instructions, 0010 and 0011. And those are going to be moving the accumulator to the H register, moving the accumulator to the L register. Okay. And basically what these two instructions are going to do is they're going to control the write enable port on our H register and on our L register respectively. Okay, so in our decode logic, we need to recognize this 0010 instruction, and then we need to take that instruction and generate a write enable bit, or a write enable, yeah, we need a write enable signal for our H register. So let's do that real quick. So basically we can pretty much use the same logic that we had before. Okay, so I'll just copy a lot of this stuff. Okay. Okay. So if I have a 0010 opcode, it's going to, this block here is going to decode my 0010 opcode and generate this output here, which is going to be the H write enable. Okay, and we're going to do the same thing for the L write enable, but that's going to be a 0011 opcode. So let's do that. going to be the L write enable signal. I'll call this capital H write enable. Okay, good. So if I have a 0011, that's going to enable my L write enable signal. If I have a 0010, that's going to enable my H write enable signal. Okay, and the idea is essentially the same for the way we decoded the other previous two instructions, the add immediate to the accumulator and the load immediate to the accumulator. Okay, so let's go back to our top level design here, and you can see that Circuitverse has created a couple of extra outputs on our decode logic, so we will just use those to control the write enable signal to our H and L registers. Perfect. Okay. Okay. So now we're in a position to write a program that uses these instructions. Okay. All right. So let's do this. Let's hook up, before we start writing our program, let's hook up a hex display to the output of our memory. All right. So the program we're going to write here, it's going to be, let me just write it out here in the annotation thing. Okay. So we're gonna load an immediate into the accumulator, and we'll put the value F into the accumulator, and then we are going to move into H from the accumulator. Okay, so this is going to transfer the value that's in the accumulator into the H register. So this is going to give us F into, so H is going to get F. It's going to get the hex value F. Okay, H is going to get the hex value F after this instruction here. Okay, and then we're going to do the same thing for the L instruction, or for the L register. So we're going to load an immediate the accumulator with, let's say, 2, and then we're going to move L accumulator, which is going to cause the L register to get 2, right? And after these 4 instructions are complete, the HL, the combination of HL, so we'll say H colon L, which is going to be together form the address that's going to go into our memory, is going to have the value hex F2, right? We put the F in the first 2 instructions, and we put the 2 in the second 2 instructions. Okay, so let's also, just so we can keep track of some of this stuff, let's also add a couple of hex displays here that are going to allow us to monitor the address that's getting asserted onto our memory. Okay, so here's our L register, and here is our H register, and together these form the index register. Okay, this is the address. Let me just write this down here in our annotation. Okay, so this is the index register, which indexes into our RAM. Okay, so at this point we can only really read from RAM, but that's okay. We can add some instructions for writing to RAM. But let's just see how this works. So first we have to write this program, right? So the first instruction is going to be a load immediate to the accumulator of F. We already have that in here. And then the second instruction is going to be move the accumulator to the H register, right? Which is, if I come back here to my decode logic, move accumulator to H is 0010. So that's going to be 20, right? And then the next instruction, right here, I could just actually write this down. The opcode for this is going to be hex 20. Okay? The opcode for this oh, I'm sorry, 1F is the opcode for the first instruction, right? 1F, and then the opcode for this is 20. Let's see here, and then the next one is going to be load immediate to the accumulator 2. So this is going to be the opcode for this is hex 12, and then moving the accumulator into the L register. The opcode for this is going to be hex 30. Okay, so let's just program this into our memory. All right, so we have 1F20, and then it's going to be 1230. Okay, and that should, after we run those first 4 instructions, that should give the index register the value of hex F2. All right, let's get after it here and see what happens. So first we'll reset the processor. Make sure that everything starts out at value 0. And now you can see we're asserting a program index of 0 into our program memory. So we're going to read the first instruction out of our program memory, and you can see that instruction encoding is 1F, and that encoding is going to be this, that codes for this instruction load immediate to the accumulator F. Okay, so if we click the clock button real quick here, you'll see that the accumulator gets the value F. Okay, and then the next instruction 20 is going to be for transferring the accumulator into the H register. So let's click the clock real quick there, and then of course what happened when we did that is our decode logic caused us to transfer the value from the accumulator. So here's the path it took. It went from the accumulator, right? It has the value F in the accumulator. It went up here, and then it went to our H register, to the D in of our H register, and then of course the H write enable signal was high, and that caused the H register to latch the F, right? What you'll notice here though is that this output of this accumulator actually goes to a lot of different places, right? It doesn't just go to the ALU anymore. It's now also going to the H register and to the L register. So why didn't the L register also latch that F when we executed this instruction 20, right? Because we have this 20 instruction. If we go here, let me just go back to the 20 instruction, right? So if we're at this 20 instruction, the output of the accumulator is F, right? And this accumulator value is getting fed through this path here up to the L register, right? If you don't believe me, let's just hook up a hex display here and see what is the input to our L register. And there you go. Our input to our L register is F, okay? So why is it that after we execute this instruction, why is it that the L register doesn't also get the F that's going into its D in port? Okay? Well, the reason for that is that only the H register's write enable is enabled. Okay, the H register's write enable is a 1 for this instruction. The L register's write enable is a 0. Okay, so what's going to happen here, if you remember from our first video on this topic, basically what's going to happen is, because we have a 0 on the write enable port, even though we're clocking in new data to this register, this register is going to ignore the data because its write enable pin is a 0. Okay, so even though the accumulator's output is going to a bunch of different places in this processor, only one of those places, or only one of those inputs that it's going into, is actually going to latch the new value. Right? And the reason that we can ensure that using the decode logic, by just making sure that the decode logic makes sure that only one of these write enable ports is going to be enabled for any particular instruction. Okay. All right. Okay, so now we're on the 20. So if we clock this thing in again, we'll see that the F gets latched into this index register. Okay, so the next instruction is going to be another load immediate into the accumulator. That's a 1-2. It's coded for this by this 1-2, right? And that's going to cause the accumulator to get the value 2. So if we click the clock, we'll see that the accumulator gets the value 2. And then the final instruction of our program is a 3-0, which is going to cause the accumulator to take the 2 and transfer the 2 this time to the L register. And if you look at our wires, you can see that this time the L register has a write enable of a 1, right? The write enable is active on the L register, not on the H register. So this time the 2 coming from the accumulator going through this path is going to get latched by L, but it's going to get ignored by H. Okay, so let's hit the clock one more time. Bam, and now you can see that the address, the index register, is now set up as F2. Cool. Okay, so now all we need to do is we need to figure out a way to store the accumulator into the memory somehow, right? So we didn't never actually come up with an instruction that can store the accumulator value into memory. All right, so basically what we need to do is we need to enable this write enable port on our memory with some instruction. Okay, so we can go and do that real quick. It won't take too long. So if we go to the, let's add a new instruction encoding here to our list. We'll make it 0100. This is going to be basically move the accumulator to, we'll call it the H:L register, right? So this is moving so this is going to be storing the value of the accumulator into memory at the address specified by H:L. Okay. Okay. So let's do that. So we will so this is going to be moving the accumulator to H:L, and this is going to be, this thing is going to be the mem write enable. Okay, this is going to be the write enable port on our memory. So let's go back to our top level. Now we have a mem write enable here. So I will run a control signal down here. Oops. Look it up. Okay, so 0100, the instruction 0100 is now going to code for storing the accumulator's value into memory. Okay, so let's do this. Let's add 2 more instructions to our program. So the first instruction we're going to add is we're going to load immediate value into the accumulator, new immediate value into the accumulator. We'll say we'll load the value 3, okay? And then the last one, we'll do a move of 2 H:L of the accumulator, okay? So this one is going to get coded for by hex 13, and this one's going to get coded for by hex, I think it's 40, let's say. Okay. So 13 here and 40 there. Alrighty. So we'll reset the processor. Oh man, here we go. Okay, we'll reset the processor, and we'll start back over at the beginning. Okay, so it's the same kind of program basically. 1F causes us to get an F into the accumulator, and then the 20 causes us to transfer that F into the H register. Okay, so now our H register is F0, And then 1, 2 causes us to get a 2 into the accumulator. And then 3, 0 causes us to transfer that into the L register. Now 1, 3 is going to get us a 3 into the H register, into the accumulator. And 4, 0 is going to store that value into RAM. Okay, so now we have stored our value into RAM. And you can see that at address F2, we have the value 3 in RAM. Okay, so the last instruction that I'd like to add here that's related to memory, at least for now, is going to be loading the accumulator out of memory. So we just stored the value from the accumulator into memory, and then the next thing I'd like to do here is to just load the value of accumulator out of memory. Okay, so we're going to use the address in the HL register, right? This is called the index register. We're going to use this address to address into memory the same way as we did for the store. But what we want to do is we want to, instead of writing the value of the accumulator into the memory, right? So the data in from the accumulator, instead of the data in coming from the accumulator, now what we're going to do is we're going to have the data out from the memory going and becoming the data in for the accumulator. Okay. This is fairly straightforward. What we can do is basically this mux, let me just zoom in a little here. This mux right here controls the input, the data in input to our accumulator. All right, so basically what we need to do is we've already used both of the ports on this mux though, right? So if we want to add a third data input source for our accumulator, we need to get a bigger mux. Okay, so we need this mux to be we need more input ports on this mux. So we can easily do that, right? If we just change the control signal size of this mux to be 2 bits instead of 1, just watch the mux when I push that. There we go. And now you can see that the control signal size input became 2 bits instead of 1. Okay, this is good. So basically what we're going to do here is the 0, 0 input to this mux is going to come from the from our ALU, just as before, and then the 0, 1 input to the mux is also going to come from our immediate value in our instruction, just as before. But we're going to add another input here, which is going to allow us to take data from our RAM and run it back through this mux here. So we're going to take the output of our RAM and we are going to bring it and allow it to be one of the inputs to this mux. Okay, cool. So now we have 3 possible sources for data that are coming into the D in port of our accumulator, right? It either comes from the ALU, if we're doing an add instruction, an add immediate to the ALU, or it can come from the immediate value from the instruction, or it can come from RAM. Okay, and so now, and what you'll notice with this mux, the thing about this mux is that since we have 4 possible input signals to this mux, we need 2 bits to tell the mux which input signal, 0, 1, 2, or 3, should be routed to the output. Okay, so we need a 2-bit control signal here. Right now, this mux, or previously I should say, we were only using a 1-bit control signal, but now we need a 2-bit control signal. Okay, so, all right, so let's do that. So we're going to convert, what we're going to do is we're going to use a splitter here that's going to take a 2-bit signal and split it into 2 1-bit signals. All right. Okay, so here's our 2-bit control signal to our mux. Okay. All right, so now what we're going to do is one of those control signals is going to come from our decode logic, and that's going to be the load immediate to the accumulator. Okay. And then the other control signal is going to come from the decode logic, which is going to which is going to be a decode signal for our load the accumulator out of RAM. Okay, so we need to add a new instruction before we do this. We need to add a new instruction to our instruction opcodes here. Okay. This is going to be move RAM H:(L) into the accumulator. Okay. All right, so let's do that. Okay, so this move from RAM to the accumulator is going to be coded for by the opcode 0101. Okay, and then this is going to be, let's see here. This is not going to be memwrite enable. This is going to be like, we'll call this mux from, or accumulator from mem. How about? Okay, so this is going to allow us to send the, we're going to send the value from memory, which is coming from on this blue trace here, into the accumulator on port 2. Okay, so this is our accumulator from mem. All right, this is starting to get a little messy here, so I should probably do some wire cleanup here so I don't accidentally cross my wires. But I might do that off screen so that you guys don't have to watch me sit here and do that. Okay, so now we're going to have a new instruction, 0101, which is going to allow us to load a value out of memory into our accumulator. Okay, so I'm going to stick with my current program here. The current program basically just puts the value 3 into memory address F2, so we'll just hang on to that for now. And then what we're going to do is we'll clear the accumulator. We'll write 0 to the accumulator. So we'll say, I think that instruction is 1F, or excuse me, 10. Isn't that right? Let me just try this real quick here. It's been a couple of days since I've looked at this. Yeah, that's right, 10. Okay. All right, so that's going to set the value, that instruction 10 is going to set the value of my accumulator to 0, which you can see happened here. And then what we'll do is we will write the value, we'll read the value back from memory to our accumulator. Okay, and to do that we're going to use this instruction that we just created here, this move H:(L) into the accumulator, and the opcode for that is 0101, which is 5. Okay, whoops. Okay, so we're going to say the opcode here, we'll say that's 50. Okay, that's the opcode. All right, let's try it. So we're going to reset, and then we'll just clock some instructions here, run the same program, we'll store the 3 into memory, and then we're going to clear the value of our accumulator. And now after we execute this next instruction here, this 50, this should cause us to load the value out of memory. Let's just check the decode logic here real quick. So the opcode should be 5. So this is I think I messed up the coding for this thing here. It should be the NOT gates are backwards, I think. They're shifted over, so just give me 1 second here. I apologize for messing this up. Okay, there we go. So now we're this is the opcode 0101, which is 5. So that's going to activate this accumulator from memory thing, which is going to cause us to take the value of the accumulator, route it through this mux here, and now you should see if we just hover over this, hopefully it'll work. We should see that the value of this signal here is a 3. Should be a 3. Now let's just see if it works if we clock it in. There we go. We clocked it in, and that instruction caused us to load the 3 that was being read out of memory through this mux here and then back into the D-in port of the accumulator. All right, cool. So now we can actually load values from memory and store values into memory. Okay, so that gives us the ability to use things like variables and do all sorts of cool stuff like that. All right. So the next time, the next video, we are going to either do branches, or we're gonna start worrying about how to add things, how to add 2 registers together. Right? It would probably be a good idea if we could add at least one of the H or the L registers to the accumulator, just so that we have a couple of possible registers that we can use. But we'll do that next time.